Hello and welcome to another edition of the Integrated Science Intervention Program for Senior High Schools. Today's topic is Conductors, Insulators and Semiconductors. My name is Kisiwa Edu. To start us off, watch this video carefully and observe what is happening. Answer the questions on the slide.
Copper. Hook it up and yes, it's a conductor. How about this piece of plastic? Flip the switch, nothing happens. It is going to be an insulator. Now we move on to another piece of metal. It's aluminum. Flip the switch, and yes, it is a conductor. Now, how about some wood? Hook it up, flip the switch, nothing happens. So it is an insulator. After the block of wood, let's try this. How about we try a Sharpie? It's plastic, it's hooked up, we go to the switch, and nothing happens. So it is an insulator. How about this? Let's try some water. I've got two nails hooked in, I flip the switch, nothing happens. Well, let's modify the water slightly. Let's add some salt. As I add the salt, I pour it in, I go back to the switch. What do you think? Is it going to change? I hit the switch, and yes, it is now a conductor. The salt allows the electrons to move freely. Next, let's try this screwdriver. The reason why I use this, I have plastic on one end, metal on the other. I flip the switch, nothing happens. But now, if I move it to where it is touching metal only, it's now a conductor. So the plastic helps insulate it.
Welcome back. Why did the light bulb go off when the wood was used? You are right, the wood is an insulator. Why did the light bulb stay on when the metal rod was used? Yes, the metal rod is a conductor. In our lesson today, we are learning to classify materials into conductors, insulators, and semiconductors. We will explain doping, describe the formation of p-type and n-type semiconductors. To start us off, we'll classify the materials into conductors, semiconductors, and insulators. Later, we'll look at doping and the formation of p-type and n-type semiconductors. Some of the keywords we'll encounter in our lesson today include electric current, conductors, insulators, semiconductors, intrinsic semiconductors, extrinsic semiconductors, doping, dopants, trivalent, and pentavalent. So what are insulators? Insulators are materials that do not allow electric current to flow through them easily. Like we saw in the video, the wood did not allow electric current to flow through it, and so the light bulb stayed off. Here are some examples of insulators. What are conductors? Conductors are materials that allow electric current to flow through them easily. Metals are good conductors of electric current. But how much a metal conducts current differ from one metal to the other. Impure water can also conduct electric current. Here are some examples of conductors. What are semiconductors? As their name implies, semiconductors are materials that conduct current, but only partly. That is, they behave partly as conductors and partly as insulators. Their ability to allow electrons to flow through them depends on temperature. Now let's have a quick look at this video to see what we are talking about.
The light stays off, so you might think the silicon's an insulator. But what if I heat it up? Thank you. It lights up. The silicon is insulating at room temperature but conducts electricity when it's very hot. It's a semiconductor.
Welcome back. Why do semiconductors behave the way they do? To understand how semiconductors work, we must first understand a little about how electrons are organized in an atom. All semiconductors have 4 electrons in their outermost or last shell. We call these electrons valence electrons. These electrons are the ones that form bonds with neighboring atoms. These bonds are called covalent bond. So we see in the picture a silicon atom with the 4 outer electrons. Silicon is an example of a semiconductor, and so is germanium. Now, inside the silicon atom, the outer electrons are shared between neighboring silicon atoms. This sharing creates a silicon crystal. We see the covalent bonds shown in the crystal on your screen. At high temperatures, some of the outer electrons gain energy and break free from these bonds. The movements of these electrons create vacancies we call holes. These holes are positively charged. Semiconductors in their crystal form are referred to as pure semiconductors or intrinsic semiconductors. Now, in the picture, we see when heat was applied to the pure semiconductor, the electrons gain some energy and are now out of the bonds, creating a hole. The free electron and hole pair are what conducts electric current in a pure semiconductor. This electron-hole pair is referred to as charge carriers. Now let's see a video that summarizes what we have said so far.
Conductors are known as intrinsic semiconductors. The atoms of intrinsic semiconductors are closely grouped together in a crystalline pattern called a crystal lattice. Let us consider the crystal lattice of silicon. This is a diamond-like structure. Each atom is surrounded by 4 nearest neighboring atoms. We know that each silicon atom has 4 valence electrons. In its crystalline structure, every silicon atom shares one of its 4 valence electrons with each of its 4 nearest neighboring atoms and also takes share of 1 electron from each of its neighbors. These shared electron pairs form covalent bonds. The figure schematically shows the 2-dimensional representation of a silicon structure at low temperatures. It shows an idealized picture in which all the covalent bonds are intact. As the temperature increases, more thermal energy becomes available to the valence electrons. As a result, some of the electrons may break away from the covalent bonds, thereby becoming free electrons. These free electrons contribute to conduction. Such breaking away of an electron from a covalent bond creates a vacancy in the bond as shown. If the free electron carries charge -q, it leaves a vacancy with an effective charge +q. This vacancy with the effective positive electronic charge is called a hole. An electron from the nearest covalent bond escapes and fills the hole, thereby creating a hole at a new position. The process continues, and this way the whole behaves as an apparent free particle. Thus, in intrinsic semiconductors, there are two types of free charge carriers: electrons with a negative charge and holes with a positive charge.
Welcome back. The question now remains, how then do we make the semiconductor have electrons and holes to conduct current without heating them? So now we look at making a semiconductor a good conductor without heat. This is possible by adding a different element to the semiconductor. So in our picture, we see an example of a germanium crystal. On the picture, we also see a different element, P or phosphorus. The process of adding a different element to a pure semiconductor in order to improve its conductivity is called doping. The element added to a pure semiconductor to make it impure is called an impurity element or a dopant. So in the case of the picture we saw, the phosphorus is the dopant. And after the phosphorus is placed or replaced with one of the germanium atoms, then we have a doped semiconductor, like you can see in the picture. Doping makes the semiconductor impure. An impure semiconductor is called an extrinsic semiconductor. Now, we look at extrinsic semiconductors. A pure semiconductor can be doped in two ways. First, you can dope it to have more free electrons than holes. This type of extrinsic semiconductor that results from this kind of doping is called a negative type semiconductor. Simply put, an N-type semiconductor. The negative stems from the fact that the majority charge carriers in this kind of semiconductor are electrons. And as we all know, electrons are negatively charged. Secondly, we can dope a pure semiconductor to have more holes than free electrons. This type of extrinsic semiconductor that is created is referred to as a positive type semiconductor. In other words, P-type semiconductor. The name positive comes from the fact that the majority charge carriers in this type of extrinsic semiconductor are holes. And like we know already, holes are positively charged. So now, let's create an N-type semiconductor. An N-type semiconductor is created when a pure semiconductor is doped with a pentavalent atom. What we mean by pentavalent atom is an atom that has 5 electrons in its outermost shell. These pentavalent atoms belong to group 5 on the periodic table. Can you name any of them? Very good. So examples include arsenic, antimony, phosphorus. Now let's quickly have a look at this animation that shows how N-type semiconductor is created. Welcome back. Let's go ahead and create a P-type semiconductor. This is done when a pure semiconductor is doped with a trivalent atom. What we mean by a trivalent atom is one that has 3 electrons in its outer shell. Trivalent atoms belong to group 3 on the periodic table. Can you name any 2 of group 3 elements? Very fine. Well done. Some examples include aluminium, gallium, boron, and indium. Now let's quickly have a look at this animation too to see how a p-type semiconductor is created. We have come to the end of our lesson. What have we learned today? In today's lesson, we have classified materials into conductors, insulators, and semiconductors. We have explained doping and described how an N-type and a P-type semiconductor is formed. For your task this week, differentiate between a P-type and an N-type semiconductor. In our next lesson, we will learn when an N-type and a P-type is put together to form a diode. Until then, it's bye-bye.